Hello everyone, this is Dr. Amudha, Associate Professor, Department of Science and Humanities Physics, RMD Engineering College. In this video, I am going to talk about in detail about this classical free electron theory. Based on this classical free electron theory, we are going to understand the derivation for the electrical and thermal conductivity of metal. So if you see this picture, the conductivity of the insulators, semiconductors and metals are being shown. So if you see here, the metal has a high conductivity compared to the other two materials like semiconductors and insulators. So it has the value of 10 to the power of 4 uh, to 10 to the power of 8 ohm inverse centimeter inverse. Conducting materials are being classified based on the conductivity like zero resistive materials, low resistive materials and high resistive materials. Zero resistive materials will have a high conductivity, and some of the examples are gallium, niobium, etc. And these materials will conduct electricity at almost with a zero electrical resistance below the transition temperatures. And they are used for saving energies in the power systems, superconducting magnets, memory storage elements, etc. Then comes this low resistive materials. Examples are this silver, aluminum and their alloys. Most of the metals are coming under this category. They have a high electrical conductivity. And they are used as a conductors, electrical devices, electrical power transmission and distribution, winding wires in motors, transformers, etc. Next comes this high resistive materials. Some of the examples are tungsten, platinum, nichrome, etc. They have a high resistivity and they have a low temperature coefficient. So these materials are mostly used as a heating elements, resistance thermometers, manufacturing of resistors, etc. So let us see some of the basic terminologies. Conductors, most of the metals are called as a conductors, and they have a high electrical and thermal conductivities, and they are called as a low resistive materials. Now let us understand the meaning of this bound electrons and the free electrons. Bound electrons are the electrons which are bound to the parent nucleus. They have a strong bonding and they are very near to the nuclei. Whereas the free electrons are far away from the parent nuclei, and they can move easily throughout the solid when they are being detached. And when they are free to move, they are called as a free electrons. So this is a picture. It shows you the free electrons and the valence and the bound electrons. So free electrons are the electrons which are completely free and detached from the bonding. And if you see this is a nucleus, positive charge, and the electrons are having the negative charges which are distributed in the various orbits. Those electrons which are very close to this nucleus are called as bound electrons. Mostly the valence electrons are the electrons in the outermost orbits. Once they are being detached from the nucleus, they are called as free electrons. The conducting properties of the solid does not depend upon the total number of electrons available in the solid. It is only depending upon the total number of valence electrons that is taking part in the conduction. Those electrons which are detached from the orbits and they are taking part in the conduction, they are called as a conduction electrons or the free electrons. So in metal, the number of free electrons available is proportional to the electrical conductivity. Greater the number of free electrons, greater will be the electrical conductivity of the material. So here this picture shows you the difference between valence electrons and the free electrons. So valence electrons are the electrons present in the outermost orbit. So whereas free electrons are the electrons which are not attached to an atom. They are detached from the orbit. And here they have a less attraction. The valence electrons will have a less attraction towards the nucleus. Whereas the free electrons will not have any attraction towards the nucleus of the atom. And these valence electrons are responsible for chemical bonding, whereas these free electrons are not responsible for chemical bonding. The valence electrons cannot conduct heat and electricity, whereas the free electrons conduct the heat and electricity. The number of valence electrons is an elemental property, whereas the number of free electrons in lattice is a lattice property. This slide shows you some of the examples of the conducting materials and the resistivity values at 20 degrees Celsius. Now here, the electron theories of solid. These theories are applicable for both metals and non-metals. It explains about the behavior of conductors, semiconductors and insulators. And also it explains about the electrical, thermal and magnetic properties of solid. There are three stages at which the electron theories have been developed. At stage 1, it is called as the classical free electron theory. It was developed by Trude and Lawrence in the year 1900. According to this theory, metal consisting of free electrons and the electrons in this metal, it obeys the laws of classical mechanics. Second stage is called as the quantum free electron theory, and it was developed by Sommerfeld in the year 1928. According to this theory, the electrons moves in a metal which has a potential and the electrons obeys the quantum laws. Third stage is the band theory observed theory. It was developed by Bloch in the year 1928. According to this theory, the electrons are not moving in a constant potential as assumed by the Sommerfeld. It is moving in a periodic potential provided by the lattice. And this theory is also called as a band theory of solid. And only in this theory, the origin of band gap, effective mass of electrons, and other special features have been introduced. And this is also called as a zone theory of metal. Now let us see the assumptions of the classical free electron theory. In metals, there are large number of free electrons moving freely within a metal. The electrons revolve around the nucleus in the atom. The second point is the free electrons are assumed to behave like a gas molecules. Here the electrons are called as a electron gas. It obeys the kinetic theory of gases, and the mean kinetic theory mean kinetic energy of free electrons is equal to that of the gas molecules at the same temperature, that is equal to 3 by 2 kBt. Next, the electrical conduction is due to the motion of free electrons only. Then the positive ion cores are at the fixed position, and these free electrons, they move, they collide with one another and also with the ion core. Then you can see the picture. Under normal conditions, you can see the positive ion cores are fixed in the position. The electrons are moving, free electrons are moving randomly in all directions, collide with one another. And whereas if you see the picture B, this is the electrons' behavior in the presence of electric field. The electrons are acted upon by the force and they are being drifted in one particular directions, whereas the metal ions will be fixed in the lattice. Okay. The electric field is applied to the metal. Then you can see that the electrons are drifted in one particular direction. The repulsion between the electrons is negligible. The electric field is applied to the metal. The free electrons are accelerated in the direction opposite to that of field applied. You can see that if the field direction is from positive to negative, then you could see the electrons are directed towards a positive terminal. Now you could see in this GIF before the application of field and after the application of field how the electrons are behaving. Now you can see before biasing, the electrons are moving randomly in all directions, collide with one another and also with the walls, whereas after applying the biasing, you could see the electrons are drifted towards a positive terminal. Now let us go into detail about the classical free electron model. It was first proposed by Trude and then it was extended by Lorentz in the year 1909. Principle. According to this theory, metal consisting of a very large number of free electrons These free electrons can move freely throughout the volume of the metal. They are fully responsible for electrical conduction in the metal. Explanation: when an atom consisting of a central nucleus with a positive charge surrounded by the electrons, and the electrons which are in the innermost shells are called core electrons, and those electrons which is in the outermost shell are called as. Now let us see, in the absence of field, how the electrons are behaving. In the absence of field, you can see the picture. The electrons move randomly everywhere in all directions. They collide with one another and also with a positive ion core. This collision is called as a elastic collision. Why? Because there is no loss of energy. Next, in the presence of field, you could see that the electrons get some energy from the applied field and they begin to move towards the positive terminal in the direction opposite that of field applied. So the electrons are assumed to be a perfect gas and they obey the law of kinetic theory of gases. Now let us go into the expression for the electrical conductivity. We know that in the absence of electric field, the motion of electrons in the metal move randomly in all directions. When the electric field is applied, the electrons move in the opposite direction in the applied field with a velocity Vd, and this velocity is known as a drift velocity. Now let us go by the important definitions now. First is the drift velocity. It is denoted by V suffix t and it is defined as the average velocity acquired by the free electron in a particular direction due to the applied electric field. So the drift velocity Vd is defined as the ratio between average distance traveled by the electron and the time taken. So the average distance is denoted by lambda and the time taken is tau. So Vd is equal to lambda by tau and the unit is meter per second. Then the mobility, the symbol is mu. It is defined as the drift velocity acquired by the electron per unit electric field. Then mu is equal to V suffix t by E, Vd by E and the unit is meter squared per whole second. Then comes this definition mean free path. It is defined as an average distance travelled by the electron between the successive collision and this is called as a mean free path. Now next we move on to this mean collision time or the collision time. It is denoted by tau c and it is defined as a time taken by the free electrons between the two successive collisions. So lambda by Vd is equal to tau c and the unit for this is second. Now next comes this relaxation time. It is denoted by the symbol tau and it is defined as a time taken by the electron to reach the equilibrium position from the disturbed position in the presence of the electric field. So lambda by Vd is equal to tau and it is measured in second. Lambda is the distance travelled by the electron. So you could see, I already explained in the absence of field, in the presence of field, how the electrons are behaving. Now then comes this important definition, current density. It is defined as a current per unit area. So it is denoted by J. J is equal to I by A and the unit is ampere per meter square. Then comes this electrical conductivity. The symbol is sigma. It is defined as the quantity of electricity flowing per unit area per unit time at a constant potential gradient. And it is calculated to be sigma is equal to Na squared tau by m, ohm inverse meter inverse. Now let us see the derivation for the electrical conductivity. First consider a metal piece AB of length L and V be the potential applied. Then the current density J is equal to minus NeVd. Okay. Now I am going to make a substitution for this drift velocity. So the acceleration will be equal to drift velocity by the time taken. Here the A is equal to Vd by tau. So Vd is equal to A into tau. Next, the force due to the electric field is F is equal to minus E into E, where minus E is a charge of electron. But this force due to the electric field can be obtained by the Newton's second law of motion. So F is equal to m into A. Equating this 3 and 4, we get acceleration to be minus E by m. But what is drift velocity? Drift velocity is nothing but
A into tau. So minus E by M into tau. Let this be expression number 6. Substituting expression number 6 in 1, we get J is equal to N minus E is already there. So in the place of VD, I am going to substitute. So minus E by M into tau. But what is Ne squared E tau by M? I'm going to equate with this Ohm's law. Microscopic Ohm's law is J is equal to sigma into E. Equating 7 and 8, we get sigma is equal to Ne squared tau by M. So this is the electrical conductivity of the metal according to this classical free electron theory. So comparing the 7 and 8, we get this expression. Now other definitions you should know. Mobility is drift velocity by the electric field, and if you substitute all the units there, you will get this unit for mobility as meter square per volt second. Because what is electric field intensity? It is the potential by the distance. Volt per meter is a unit, and drift velocity is meter per second. So when you substitute everything, you get meter square per volt second. Now the current density is J is equal to sigma E. You know this expression. You also know this J is equal to NEVD. When you equate these two equations, you get a new relation. Sigma is equal to NE. Now I already explained how you are getting the expression for the electrical conductivity. We have substituted everything and we got the expression as sigma is equal to Ne squared tau by M. Now we move on to the next definition, which is the thermal conductivity K. Thermal conductivity is defined as the amount of heat flowing per unit area per unit time, which maintains a unit temperature gradient, and the unit is watt per meter per Kelvin. And this dt by dx in the formula is nothing but the temperature gradient, the variation temperature with respect to distance. So the heat flows from the hot end to the cold end. Here Q denotes the amount of heat energy and K denotes the thermal conductivity. Now you could see this GIF where when the metal piece is taken and heated at one end, you could see that due by collision, the heat is being transferred from hot end and cold end. You could see from one side the blue color ball is turning into red, by which you can understand the heat is being transferred from hot end to the cold end. Now let us go into the derivation part now of the thermal conductivity. So here it is, we know that electrical conductivity is amount of electrical energy flowing per unit area per unit time, which maintains a unit potential gradient, and the unit is ohm inverse meter inverse. Whereas when you define the thermal conductivity, it is defined as amount of heat energy flowing per unit area per unit time, which maintains a unit temperature gradient. Now, if you find the thermal conductivity of the material, it may be due to the presence of lattice vibration or it may be due to the presence of electrons. So we take only the total value. K total is equal to K electron plus K photons. Now let us take for a metal. Metal, the total thermal conductivity is mainly due to the conductivity of electrons. Whereas when you take semiconductors, the thermal conductivity is both due to the electrons and photons. Whereas when you take an insulator, the total conductivity is only due to the lattice vibrations. Now let us consider the metal piece AB. And let us consider cross-sectional area at C. The total length be 2 lambda and this cross-sectional area is at the mean free path region. Let A be the hot end and B be the cold end. So the heat is flowing from the hot end to the cold end. Let N be the number of conduction electrons and B be the velocity of the electrons. And here the velocity is a thermal velocity, not the drift velocity, and Kb is the Boltzmann's constant. So found the kinetic theory of gases. So we just proceed now. So this already I explained to you. So when you heat at the hot end, the heat is transferred from hot end to cold end. Let N be the number of electrons crossing per unit volume, which is electron density, and V is going to be the thermal velocity. Now, we assume that there is a fixed direction and there is equal probability of electrons traveling in each direction. So here we wanted to find out the amount of heat traveling from NA to NB. So the total number of electrons moving with the velocity V throughout the metal is N into V. But we wanted to find out for one direction how many number of electrons are crossing. The number of electrons crossing per unit area per unit time in one dimension is going to be NV by 6. NV is the total number of electrons. If you have 6 direction, I wanted to find out for one direction how many electrons are going. It is NV by 6. Let us call this as equation number 3. Now next, the average kinetic energy of an electron at the hot end at the temperature T1 is equal to half mv square is equal to 3 by 2 kb T1, where T1 is the temperature of the hot end. Let this be expression number 4. Then the heat energy transfer per unit area per unit time from A to B across C is given by the formula. I am going to take this energy as Q1. Q1 is equal to the number of electrons crossing in one direction and the kinetic energy of the electron. When you take the product, you get so much of heat energy which is being transferred from A to B across C. Now, substituting equation 3 and 4, we will get Q1 is equal to 1 by 6 NV into 3 by 2 kB T1. On simplification, you get Q1 is equal to 1 by 4 NV kB T1. And next, similarly, the heat energy transfer from B to A across C. There is also some kind of dissipation of energy in the opposite direction. I am going to take that heat energy as Q2. See, applying the same formula as before, it is equal to the product of number of electrons from B to A and the kinetic energy of electron at B with the temperature T2. Then we will get, since it is going in the opposite direction, we have to put a minus. So Q2 is equal to minus 1 by 6 NV into 3 by 2 kB T2. Let this be expression number 6. So having got this value Q1, Q2, we are next going to find out the net heat energy transferred from A to B across C per unit area per unit time. So which is the sum of these two. So Q is equal to Q1 plus Q2, 5 plus 6. So Q is equal to 1 by 6 NV into 3 by 2 kB T1 minus 1 by 6 NV into 3 by 2 kB T2. So when you simplify, you get Q as 1 by 4 NV kB into T1 minus T2. Let this be equation number 7. Now substitute 2 in equation number 7. Now substituting 7 into, we get the thermal conductivity per unit area per unit time to be K is equal to Q into 2 lambda by A into T into T1 minus T2, where Ta is 1 meter squared and T is 1 second. Then we will get Q, rearranging the terms, 1 by 4 NV kB T1 minus T2. Okay, when you substitute back into the formula, we end up like K is equal to 1 by 2 NV kB lambda. Okay, so we are going to make a substitution to find the Wiedemann-Franz law. Okay, here I am going to substitute this lambda in terms of tau. So what is tau? Tau is equal to tau c for metal, and that is equal to mean free path by the velocity. So when I rearrange, I will get lambda to be tau into v. When you substitute, you get the k value to be 1 by 2 nv squared kb tau. Let this be equation number 9. Now we are going to discuss about Wiedemann-Franz law. Okay, the ratio of the thermal conductivity to the electrical conductivity is directly proportional to absolute temperature. If I want to remove the proportionality, I introduce a constant called lambda. So K by sigma is equal to L into T, while L is the Lorentz number. Okay, the value for the Lorentz number is 2.44 into 10 power minus 8 watt ohm per Kelvin square, where L is called as a Lorentz number at the temperature of 293 Kelvin. Now, we know the equation. I am going to prove that K by sigma is equal to LT. So let us see the value for K. Let us see the value of sigma. We make a substitution. So we know we have just now calculated sigma is equal to Ne squared tau by M. And what is K? K is equal to 1 by 2 Mv squared Kb tau. Substitute these two equations in the LHS of this Weidmann-Franz law. Then when you substitute, bring this denominator to the numerator, and in the place of half mv squared you substitute the kinetic energy, which is 3 kBt. When you substitute and rearrange, you get back the expression as k by sigma is equal to 3 by 2 kb by e the whole square into t. What is 3 by 2 is a constant, kb Boltzmann's constant, e the charge is a constant, so which can be taken again as L. So what is L? L is equal to 3 by 2 kb by e the whole square. Hence k by sigma is equal to L into T, which is proved that k by sigma is directly proportional to the absolute temperature. And all this I have already discussed. What is the energy of electron at A, what is the energy of electron at B, and how there is an equal probability of electrons moving in all the 6 directions, and what is the amount of electrons traveling in one direction. All that I already discussed. So all this I have discussed. We have even defined the Weidmann-Franz. We already discussed. I am going to define the Weidmann-Franz law. It is the ratio of thermal to the electrical conductivity is directly proportional to the absolute temperature. So K by sigma is equal to L into T. I am going to prove. So we have made a substitution, already I discussed with you, and then we end up with K by sigma is equal to L into T. Now when you take the Lorentz number, L is equal to 3 by 2 kb by e the whole square. Kindly substitute the value for the Boltzmann's constant, which is 1.38 into 10 power minus 23, and for the charge E is equal to 1.6 into 10 power minus 19, and you end up with the Lorentz number as 1.12 into 10 power minus 8 watt ohm per Kelvin square. Whereas when you see for the quantum theory, the value is the different, because the electrons moves in a periodic potential. So M should be replaced as M star. Then you will get exactly the L value, 2.44 into 10 power minus 8 watt per Kelvin square. There the Lorentz number is not 3 by 2 kb by e the whole square, it is pi squared by 3 kb by e the whole square. This is again a drawback of classical free electron theory. Now let us go into the detail of both the drawbacks of classical free electron theory. First point is it is a macroscopic theory. Next, according to the classical theory, all the free electrons will absorb energy, but it is not so. According to the quantum free electron theory, only few electrons will absorb energy. Next, it could not explain the Compton effect, photoelectric effect, paramagnetism and ferromagnetism. The theory cannot explain the electrical conductivity of semiconductors and insulators. The dual nature of the light cannot be explained by the classical theory. And you have many discrepancies. The experimental value and the theoretical values are does not matching for the specific calculation, Lorentz number, etc. So these are the drawbacks of classical free electron theory. When you see the success of classical free electron theory, first is it verifies Ohm's law. It is able to explain the electrical and thermal conductivity of metal. It is used to derive Weidmann-Franz law and explain the optical properties of metal. Thanks for watching.